This video is going to be a short video where I'm going to go over some of the stuff that we did at the very beginning of the exponential functions. The beginning prompt sets up a problem where we have some item. This is a hamburger that is priced at $4, but that price is increasing by 9% per year. So I asked the question, what would you multiply the $4 by so that you could figure out the price 1 year from now? The answer to that question is 1.09. Where that comes from is taking 100% plus 9%, which becomes 109, and then with the shifting of the decimal, you end up at 1.09. The reason that you do want to add the 100% onto it is that when you multiply and you multiply the $4 by that, the 4, you can think of it as being distributed to the 100% and also getting distributed to the 9%. So when you do that calculation, let me go ahead and type that in for you here. Okay, so when you type that calculation in, what it does is it gives you back the $4 plus the additional amount versus you doing something like this where you take 9%, multiply that by 4, get 36 cents, and then you add it back onto the 4. So if you just do the addition at the beginning with the 100% and the 9, then it gives you a single number you can multiply. So then for the table, what we do is just continue to multiply by that 1.09. And skipping ahead, it does complete all these values, except that last one I just noticed there. That would have been correct if we were looking for a 5. That would go in that spot. But what we really want to do is just set up a formula. So this is going to be 4. What we're doing the whole time is just multiplying by 1.09. And the way that you can show that you're multiplying by 1.09 repetitively is to create an exponent that would go with it. Okay. Oh, sorry again, talking as if that's a 5, but it could be for any time, so you don't have to do 5. You could jump all the way ahead to like 10 years. Okay, example number 1. I do want you to calculate for 5 years, and that's probably why that number was stuck in my head here. So if we just set this up, we have 4 multiplied by 1.09 to the 5th power. It should turn out to give you that. I had a different number up at the top, which kind of throws me off on that. So let's see what we actually get. Is that what I had up the top? I did. That's what I had originally. So I'm not really sure where that number came from, but there you go. You're going to get 615. All right. Here's the part where it gets a little bit confusing. Please make note of this, and probably one of the big reasons I wanted to recap this portion of it for you is that we have to be careful when we talk about increasing and also talking about like increasing, decreasing, and also when we talk about moving forwards and backwards in time. So if something is defined by an increasing percentage, you got to make sure that you continue to use that as your base number when you're multiplying. So if you get asked the question of what the value was 5 years ago, what you do is you raise it to the negative 5th power, which is going to give you that number. What you don't want to do is change the base that you're using. Like don't say, well, if it's increasing by 9% as we move forward in time, then it should be decreasing by 9% backwards. It actually doesn't work out to be the same. It's somewhat close in the answer, but it turns out to not be that. So however something is defined, if it's an increase or decrease, make sure you keep that as your base. Then as far as time, you could just look at it as a positive or a negative, there it is, or a negative exponent, which that should make sense when you think about the table, because if you're going to the right, you're going to keep multiplying by 1.09. But if I want to go backwards, right, if I want to go that direction, I would actually divide by 1.09. And when you use negative exponents, so this is pretty intense to think about here, but when you use negative exponents, things are going to flip over and give you a reciprocal, and a reciprocal then implies division. So the negative does work out and tells us just to continue to divide by 1.09. Example 2 is going to give you that other version of, okay, what if we define something as decreasing? So if the price of the hamburger is actually decreasing by 9%, that's when you can use this base here. So I take 100%, I subtract 9, get 91, which is going to give me 0.91. And then this, if I have it defined as decreasing by 9%, you can still do forwards in time, and you can even go backwards in time and find out what it used to be worth 5 years ago, even though it's decreasing. Next, we take a look at the basic graph of exponential growth and also exponential decay. Exponential growth is when something's going to be increasing by value. In the equations, you're going to be able to identify because the value that you're continuously multiplying by, the value that gets raised to power, is going to be something greater than 1. Example would be like the 1.09. The decay type functions are going to have b values that will be less than 1. Okay, so if you multiply by something that is less than 1, you always get back less in return, sort of like the 0.91. The b values cannot equal 0, because if you're raising 0 to the x power, you just continue to get 0. Nothing really happens with that one. You also can't have negative numbers, which I'll kind of avoid talking too much about that right now, but the basics are, if b is a negative power and you keep raising it to different types of exponents, you can create imaginary numbers. Okay. All right, example 3 here. The graphs, I should probably talk just a tad bit about like the shapes of the graphs. So the growth functions, they look like this. The decay functions look like that. And yes, in a way, they are actually each other's reflection over the y-axis. They do have asymptotes at the x-axis, and that's going to be consistent for the beginning parts, and then later we'll talk about how we can move them around. Each of the graphs do have very important key points. The y-intercept, okay, and then you also have a value, a point over here that's over just 1 unit. So what happens when you have 1. And the reason that these are important, that's also in the decay here, the reason that that's important is because when you raise any base, no matter what it is, to the 0 power, you always get 1. So this is a coordinate. Until we start doing a lot of transformations, this is a coordinate that you can really rely on being in every graph. The next coordinate is now unique to each one, but it's also really easy to figure out. If you raise b, whatever it is, to the first power, you're just going to get your b value, and you can plot that. So that's always a good starting point when you work on the graphs. Okay, example 3. You're going to notice here that the 0 and the 1, I went ahead and I did that in a different color because those are those 2 points that I'm really like focusing on as being very important. Okay, our function, very simple function right now, is just 2 to the x power. So if you raise 2 to the 0 power, you're going to get back at 1, and then of course if you raise 2 to the first power, you get back at 2. So I can always fill that in very quickly, and then even on the graph, I went over here and I plotted those in that pink color that's there. I also have that asymptote here at the x-axis, which would be a consistent thing here. This function is going to be a growth function because 2 is a number larger than 1. So we can expect that shape to it. The rest, you just sort of plug in numbers and you do the math here. If you take 2, and that goes in for the x, and now we're asking you to take 2 and square it, it's going to give you a 4. If we take the 3 and plug it into the function, they're asking you to take 2 and cube it, which is going to give you a total of 8. You should see, as you go through this table, that repetition of times 2 every time. So backwards, we should expect that we're dividing by 2. But in addition to that, so hopefully you look at that and you see what's dividing. In addition to that, when you raise to a negative power, it creates a reciprocal. So if I raise, let's take this one here. If I take, I was right out the side, you take 2 to the negative 3 power, you're still going to cube it, which will give you 8, but then that negative tells you to flip it over. So remember, negative exponents do not make things negative, they just flip. You need to know that rule. Negative exponents flip things. Okay, next I would take all that, I'd plot it, and I'm not going to go through all the points, but you could easily take a look at that and figure out if you need to see more from it. The domain is going to go negative infinity to infinity. That is always going to be true unless we decide to restrict the domain. It is always going to be true that it continues to expand out. So this does appear to be going to almost like a vertical asymptote, but it does not. It is continuously continuing to push out. It's kind of hard to imagine it because you got to zoom really far out just to start seeing it change a little bit, but it does continue to move out. An easy way to also look at that is we don't have any restriction on what values, like how big our values can be that we're raised to. So if we're not restricted on what we can plug in for the x's, then it's going to be all real numbers. The range is going to be slightly different. It is going to be very consistent, but you're going to notice that you're going to be bounded on one side. So in this case, you're bounded at that x-axis where the asymptote is, and then it goes up to infinity. We do use open parentheses because that is an asymptote. All right, and last here, example 4. We look at the decay version. To make things very simple, we went with the reciprocal of our other base, which was 2. And I hope you realize why using the reciprocal is a good idea for this comparison. Okay, so again, my most basic points I should count on, we have 0 and 1. We also have 1 and then our base. So those points I plotted. And you may notice that that point used to be over here when we did the 2. So I wanted to see that comparison there. The rest of this, you just sort of fill it in. Let's see, this direction, you're multiplying by 1/2 because that's your base. This direction, you're going to divide by 1/2, which, AKA, is multiplied by 2, because it's just the reciprocal of that. If you divide by 1/2, you're actually multiplying by the reciprocal, which is 2. Okay, so all those points get plotted. Your domain is still all real numbers. Your range is still going to be bounded at that asymptote. In the next couple sets of notes that you see this week, we're going to start shifting things. Those asymptotes are going to move around. The graphs are going to flip, they're going to stretch, and they're going to do some other things. This is just going to set you up for a baseline so that when we talk about how we do those graphs, I think that transition will be easier to see from there. In addition, you don't have a worksheet on this one. Just be aware, you do not have a worksheet on that. The other two are going to have worksheets. The intention here was just to get us caught up to like where we left off.